Welcome back to more screencast fun. This screencast will be our introduction to operational amplifiers. There's a schematic of one shown here, a triangle. Typically a triangle means amplifier, whether it's in optics, whether it's in electronics. A triangle can also mean a buffer as well. This device that we're going to be talking about does more than just amplify. So amplifying is one of its features, but it can also do math. It can take integrals and derivatives way better than the circuits you made just with resistors and capacitors. It can do math on circuits. It can sum. It can take logarithms, and depending on your creativity of what you put in the feedback network, it can do all kinds of things. We are going to treat this device like a black box. Inside the op-amp is at least 30 transistors or more, and one transistor, as you'll find when we get to it, is very complicated. And so putting 30 together, we treat it with golden rules. So we have these rules of how this thing works. But before we talk about the golden rules, let's talk about what the op-amp, just how you lay it out on the circuit board a little bit, or what the pins are. Open loop gain, we'll go to our golden rules, and then we'll do some examples. Okay, so an op-amp here, you see these numbers here. This is a 2, that's a 3, that's a 4, that's a 7, and that's a 6. And what we're going to use is we're going to use a package that has pins. It's DIP is what the initials are for the DIP package. The chip is going to be set across the trench in the breadboard, and you'll have to power it. This is an active circuit. So passive circuits are what we've done so far. We may have had a voltage source, but in order for the capacitor to operate, in order for the resistor to operate, in order for the inductor to operate, we didn't really need to apply power. These were passive components. An op-amp is an active device. If you don't apply power on V plus and V minus, it's not going to work. Typically what we do is we're going to put a plus 15 on V plus and a minus 15 on for V minus on pin 4. The output will be pin 6, and I'll talk about these negative and what these positives are. And so let's talk about open loop gain. Okay, here's a schematic again of an op-amp, and what we're going to talk about is open loop gain. Open loop refers to the fact that there is no feedback loop here. So what we'll see in future pictures here is we're going to actually connect the output back to the negative input to give it negative feedback. We'll talk about positive feedback briefly, but negative feedback is actually important for all the circuits that you're going to make. However, the very first circuit you're going to make is you're going to test the open loop gain. So no feedback loop at all. That's why it's open loop. It's not closed loop. What the op-amp, it's really basically it's a difference amplifier. What it does is it takes the difference between the input on the positive and negative terminal, so VP for positive and for negative, and it's going to multiply it by the open loop gain, which is denoted by A in most texts. And the open loop gain is enormous. It's on the order of 100,000 to a million, and this is important to make this device function. Here's the thing though, even though the gain is on the order of 100,000 to a million, it doesn't mean if the difference here is 1 volt, I'm going to get a million volts out here. Typically your V plus and V minus is something like 15 volts and minus 15 volts. So what that tells you here in the little box here is that, look, you can't get more than 15 volts out of the thing, and you can't get less than minus 15. So if you have 1 volt on here, that's a difference. You're going to get 15 volts, which is not a million or not 100,000, and you're basically saturating the amplifier. You're pushing it too hard where it can't reach its optimum gain. Same thing where if the difference between here is negative 1 volt, you'll go down to the negative rail. We call it the rail, positive and negative rail, the positive 15 and negative 15, and you're not going to have, again, a million gain because you're operating in a regime that's just too high of an input. So when you test this in lab, you're going to make the difference between VP and VN something like microvolts, and therefore you'll get something like volts out, and you're going to use a high resolution potentiometer of the resistor that changes to actually twiddle and change the voltage here very, very, very carefully. And you're going to measure the open loop gain. Alright, so why do we care about open loop gain? Well, basically we want this gain to be big because we're going to feed back a portion of it into the negative terminal to actually kill the gain. Alright, why the heck would you want to do that? We'll see that in just a little bit. Here's a schematic of negative feedback. You'll notice that I've dropped the power supplies, the rails here. We often do that because it's kind of understood that you're going to put a positive 15 and a negative 15 on pins 4 and 7 respectively, or 7 and 4 rather. So here's what's happening here. I haven't shown you an input yet, but you might be putting an input either on the positive or negative, or maybe even both. And what happens is if we didn't have this feedback loop here, what would happen? Vout would be huge, or it might hit a rail, like the 15 or the minus 15, or we'd have to make sure this difference is very small. What you'd like to do is you'd like to put a signal in here, and instead of getting that signal all the way to the rail or having to worry about it, you actually take some of that signal and you feed it back to the negative input, and it actually takes down the gain in a way that's controllable and usable. So the gain of this thing is really, the open loop gain is really, really high, and then you purposely take off some of that open loop gain in a very, very controlled manner, and then you have this closed loop gain that you can use to make an amplifier, or you can use to make a circuit that does math. So the point of this is, it seems kind of strange, is that you are actually, you basically are continually feeding back power into the negative input here so that this thing never hits the rail. You keep it in a very stable regime. Here's a schematic of the opposite of that. You can imagine that you have positive feedback going back, and so again, if the voltage here is even just a little bit too high, this thing will go, it'll hit 15 volts here. Alright, and then that 15 volts will be fed back, which will likely be higher than here, and so this thing will slam down and hit negative 15, which will be fed back and will hit positive 15. So what the positive feedback tends to do is it actually tends to make the op amp oscillate. So you can put a DC voltage in here, not even a signal, and it's going to flip back and forth. The output is going to flip back and forth between plus 15 and minus 15. That could actually be interesting if you do it in a very controlled way. You can actually make a function generator out of that. You could make a square wave or a sine wave out of this, or a triangle wave. So these are the basis of oscillators, which are very important in electronics. But if you're actually trying to do, like, amplify something or do math on something, this would be a terrible thing. So positive feedback often lends to kind of a chaotic circuit, and unless you put some kind of special elements on it, you won't have an oscillator. And you typically don't want an oscillator. So in the circuits you're going to build, it's negative feedback only, and you'll see how that's helpful. Now for the golden rules. These are in your book. They're also in the lab manual as well. You could probably find them on most online sources, reputable ones. And this is only for negative feedback, but there's just 2 of them, and they actually can take you very, very far. Is that the output of the op amp does whatever is necessary to make the voltage difference between the input 0. So what the circuit, this black box that we're using, is designed to do is that the output is always going to try to make VP and VN be the same. It's going to make the positive and the negative inputs be the same voltage. The difference is going to be 0. And here, this might seem kind of abstract or obtuse right now, but we're assuming that the inputs draw no current. That means that the input impedance of the op amp is infinite. That's awesome. All right, that's something you want, because now if you put the op amp as a load on something, it'll never load your circuit. All right, so effectively, and in reality it's not true, it's not infinite, but it's very, very, very big. But if these inputs really draw no current at all, then the input impedance of the op amp is infinite. Combined with rule 1, you'll see how these circuits can be used to give us gain on simple amplifiers. Let's start with the inverting amplifier. So it's called inverting because the input, it's going through a resistor first, is going into the negative input. And let me actually label those resistors. I forgot to do that as I set this up. Let's call that one R1, and let's call that one R2. Not terribly clever, but that's what we're going to do. What we're interested here, we're interested in the gain. And because there's a loop here going from the output back to the input, this will be closed loop gain. The open loop gain is something that's actually spec to the op amp. It's something that's hard to calculate. It's just kind of given with the circuit. However, the closed loop gain we can always calculate. So let's use a different color here. So what we want is we want a closed loop gain. I'm going to call it capital G. And that's going to be V out over Vn. Okay, that's the kind of thing we want to find. So let's see what's going on here. Let's apply golden rule number 1. If you remember golden rule number 1, it says that the difference between the inputs is 0. So check it out. The input here is grounded. That means this point right here is effectively ground. Let's draw a little ground in here. Weird, okay? Geez, what are we going to do with that? Well, let's calculate currents and use V in and V out and the resistors to figure out what's going on here. Okay, so what we have is we have, if this really is in fact ground over here, we have a, let's assume a current, I, is going that way to ground, all right? Oh, but check it out. There's also a V here and the ground here, so there must be a current going this way. All right, and here's the weird thing. Those currents are the same because there's no junction here. This thing, here's golden rule number 2. Look, there's no current drawn in that input. So all the current flows through here and into here. All right, they all flow into the same place. There's no junction, so even though they're going in opposite direction, they're the same. And now we can calculate that. So the I here is the same as the I here, and we know that I is just going to be Vn minus 0 over R1, and the I here is going to be, we could say, a 0 minus V out over R2, right? That's the direction of that. Or we could say V out over R2, and it's in the negative direction. So let's write that up. Basically, one of the I's here, the I for the first part, is going to be Vn minus 0, that's the ground, over R1. That's for the input side right here. That is going to be equal to 0 minus V out over R2. Wow, this is looking pretty easy here. Can you see already that Vn over R1 is equal to minus V out over R2? So let's write that over here. We have Vn over R1 is equal to minus V out over R2. Cool, and we're basically at gain. So gain, which is V out over Vn, is just going to be minus R2 over R1. What a very simple circuit. So if R2 is 10 times more than R1, you get a gain of 10. If R2 is 100 times more than R1, you get a gain of 100. You're still within the limits. You can't go over the rails. If you have 15 volts and minus 15 volts is the rails, you're never going to output more than 15. But you could, for example, have a gain of 10, put in 1 volt, and get 10 volts out of this thing. This will be our last example for this screencast. This is the second example that one usually does when learning or teaching about operational amplifiers. So here's the non-inverting amplifier, and you can see that the input is on the positive, the non-inverting input. And once again, we have feedback on the negative side here. And oh, I forgot to label my resistors again. Not a problem. Let's call this one R1 and R2. All right. So using golden rule number 1, we know that the positive input to the op amp has to be the same as the negative input. So we can label this as Vin right over here. Okay, and if you see here, this is just looks like, remember the op amp, golden rule number 2, the op amp draws no current. So if there's no current going into here, there's no current going back up into this junction. Can you see that it's just a backwards voltage divider, where if we were going this way, we go through R2 and then to ground. So this point here is V out. Let me label it down here, V out. This is V out. This point over here is V in. No current goes up here. All the current goes through here. All the current goes like this. All right, and so look, that's just a voltage divider with our V out and our V in flipped. So if it's flipped, we have V in is equal to V out, and R1 and R2 are flipped to R1 over R1 plus R2. Okay, and remember our gain is just V out over V in. That'll equal G, and that's going to be equal to R1 plus R2 divided by R1, which is going to be equal to, see if I can squeeze it in down here, 1 plus R2 over R1. Let me box that there. A little cramp, sorry about that. Let's see if we can squeeze it. There we are. So the gain is almost the same as the inverting one. Remember, the gain was R2 over R1, negative R2 over R1. It flips it, and this one is 1 plus R2. That's it for this first screencast on op amps. We'll get into more details in class and in future screencasts.